Okay. So 5.6 is all about half angle identities. 5.5 was double angle identities, so you would think logically, oh, we can just divide all those by 2 and we get our half angle identities, but that's not how it works. We get all these really weird looking half angles. These are included on the handout sheet. They are the last set of identities here next to the unit circle. Those are the ones we are going to play around with today. Now, just because we're in half angles doesn't mean we're not going to do anything else. Obviously, all the other identities are still at play. The big thing to note is that when you are dealing with half angles, there is a plus or minus in front of some of them. And that tells you it can be either positive or negative, and that depends on what quadrant our A/2 falls in. So this again goes back to that table from 1.4 where we have to know whether sine, cosine, tangent, all that stuff is positive or negative based on the quadrant that it falls into. And so your problems will always give you enough information, or if it's a very broad general example that you were playing around with, then you will leave it with a plus or minus out there. So the first 3 have the plus or minus, and then there's 2 additional tangent half angle identities that do not have the plus or minus. And sometimes they'll even be really specific and tell you exactly which identity they want you to actually use. So that's kind of nice when they do that. So total there are 5 half angle identities, but 3 of those are tangents. On to the first example because you do have them listed on your paper. So you can write them down from there if you, like me, would like to keep them in your notes in the right spot. I get it. Okay. The first type of problem that you can encounter is find the exact value of a specific trigonometric function, cosine of 15 degrees. If you plug that into your calculator, it will give you in a decimal approximation. If you know how to really use your calculator, you have a really smart calculator, you might even be able to plug that in and come up with a radical of some kind. But we are assuming that you cannot do that, and we are going to use a half angle identity in order to come up with this, because it says use a half angle. So what we're going to do is we're going to think about how can we rewrite cosine of 15 so that we can use a half angle. Well, what is 15? Like, something divided by 2 is going to give us 15. What divided by 2 gives us 15? 30. Yeah, 30. So we could write cosine of 15 as cosine of 30 degrees over 2. And the reason why you would want to do this is because it specifies that we need to use a half angle identity. And if I'm using my cosine identity, which is right here, then I have to have that as a over 2. Well, I've now written that as a over 2, and a in this case is going to be that 30 degrees. So I can finish writing out the identity because I know that it is 1 plus cosine of 30 degrees over 2. Now notice I did not include the plus or minus out in front of that. And that is because if I'm finding the cosine of 15, 15 degrees falls in the first quadrant. Everything is positive in the first quadrant. Cosine, sine, and tangent are all positive in that first quadrant, so I don't have to consider the plus or minus in this case. So now at this point, I need to know what is cosine of 30. And if you don't know, you can look at that unit circle that's on the back of the handout and figure out what cosine of 30 is. So if you look at your unit circle, and we go up to 30 degrees, cosine is going to be the x value, so that's radical 3 over 2. So I'm substituting that in. Now, at this point, I've got all kinds of wonky stuff going on. I've got a fraction and a fraction, I've got a radical and a radical, and I've got a radical in the denominator, and all of that stuff causes lots of problems. So what I'm going to do is first I'm going to just get rid of the fraction and a fraction situation that's going on up here in the top. And to do that, I would multiply the top and the bottom by 2. Because if I multiply radical 3 over 2 by 2, that's going to get rid of that denominator and simplify that out a bit for me. 2 plus radical 3 all over 4. And the nice thing about multiplying by that 2 is I actually then get a perfect square in my denominator. So instead of having to rationalize my denominator, I can just simply simplify my denominator because the square root of 4 is 2. And as much as you're going to hate it, that's it. We leave it with a radical and a radical. Because it's in the numerator, that's okay. If we had still a radical in the denominator, we would need to rationalize that in order to get it out. But we have a whole number in the denominator. There's nothing else that we can simplify or pull out. And so this is the exact value of cosine of 15 degrees, which is kind of gross. But luckily, we don't have to memorize that stuff. We just have to be able to get there. Questions on how we did that? Okay, let's do another one. Let's do a tangent one. This one, because we do have 3 different identities that we have for tangent, they did specify which one they want us to use. They want us to use the middle tangent identity. It says find the exact value of tangent at 22.5 degrees. Using tangent of a over 2 is sine a over 1 plus cosine a. So we're going to do a very similar process to what we just did with our cosine. We have tangent at 22.5 degrees. We need to write that so that we have tangent of a over 2 as something divided by 2. So basically what you need to do is take 22.5 and multiply it by 2 to know what that a value is. What is it? 45. 45 degrees, which is kind of nice. 45 plays pretty nicely with most things. So tangent of 45 over 2 is going to be sine of 45 degrees over 1 plus cosine of 45 degrees. Sine of 45 degrees is what? If you don't know, you can look at your unit circle. Sine of 45 degrees would be radical 2 over 2. Cosine of 45 degrees is also radical 2 over 2. So that means on top, we just have radical 2 over 2, and on bottom, we have 1 plus radical 2 over 2. Now I've got fractions and a fraction again. So I'm going to multiply the top and the bottom by 2 to get rid of those fractions. Because I don't like having fractions and fractions. That'll leave me with a radical 2 on top with 2 plus radical 2 on bottom. Now I do have a radical in the denominator, which is a problem. So I need to rationalize the denominator. How do I do that since I have a binomial in the denominator? That's right. We're going to do 2 minus the square root of 2. That's known as the conjugate. You multiply the top and the bottom by the conjugate, and that's where you change this middle sign right here. Everything else stays exactly the same, but you change that sign. And the reason why it works is because then when you FOIL, what happens is that middle term, which is the term that would contain the radical, is actually going to fall away. Because when you do your outer, you would have 2 times a negative square roots of 2. And you do your inner, you'd have 2 times a positive square roots of 2, which means they go away, which is really nice. So yes, we multiply it by the conjugate. So on the top, we have to distribute so that we have 2 times radical 2. And then we would have radical 2 times radical 2, which just becomes 2. On bottom, really we only have to worry about our first, which is 2 times 2, which is 4. And our last, which will be a negative 2. Because the middle terms fall away. Sorry. Here you go. So you get 2 square root of 2 minus 2 all over 2. Lots and lots of 2's in this one. Since we have one number on bottom, we can simplify with the top, meaning we're going to get radical 2 minus 1. That is the exact value of tangent of 22.5. Questions? If the rationalizing with radicals or anything like that is tripping you up, basically if the algebra portion of the trig is mixing you up a little bit, do note that in the Pearson site, when you go to your e-textbook, you actually have access to a college algebra textbook as well. And so you could open the college algebra textbook and you could go to the section on the radicals and kind of look through it. With the textbooks, it comes with PowerPoints and videos and all kinds of extra stuff that can be really helpful. So if that is something that is tripping you up a little bit, you can find resources within the trig class itself. Okay, let's look at another style of problem. Sorry, I keep moving it up and down and trying to get it to the top. This time they're going to specify which quadrant we're going to be in, and they give us a little bit of information, but then they want us to find the half angles for sine, cosine, and tangent. So they give us cosine theta is 2 over 3, and they tell us that theta has to lie between 3 pi over 2 and 2 pi. 3 pi over 2 and 2 pi would put us in which quadrant? Yeah, it put us in the 4th quadrant. But are we trying to find theta, or are we trying to find theta over 2? Like, what are they asking us to find? Like, do they want us to find stuff in terms of theta or in terms of theta over 2? Theta over 2. So we need to kind of change our parameters a little bit, because originally they're starting us with 3 pi over 2 is less than theta, which is less than 2 pi. But what we're really wanting to deal with is theta over 2. So we kind of need to divide everything by 2 to figure out our new quadrant or our new parameters. So if we divide everything by 2, we get 3 pi over 4 is less than theta over 2, which is less than theta. This is actually the quadrant or the area that we want to be concerned about. And that takes us out of quadrant 4 and puts us into which quadrant? If we're thinking about 3 pi over 4 to pi. Yeah, that takes us to quadrant 2, doesn't it? Quadrant 2 lies between pi over 2 and pi. So this is taking us to quadrant 2. Now, why is this important? It's important because we need to know whether sine, cosine, and tangent are going to be positive or negative. And if we're in quadrant 4, that's going to be different than if we're in quadrant 2. And so we have to make sure that we understand which quadrant we're in so that when we get our answers, we know whether or not we're supposed to be getting positives or negatives. Because with our cosine, our sine, and depending on which tangent we use, we do have that plus or minus out front. If we are in quadrant 2, then our sines are positive, our cosines are negative, and our tangents are negative. Remember, sine correlates to your y's, cosine correlates to your x's, and then if you have one of each of those, then obviously your tangent's going to end up being a negative as well. Okay, so let's get started with the first one. Let's look at sine of theta over 2. Now, the original identity gives us a plus or minus, but we don't really have to consider that because we know that we're going to get a positive out because we are in quadrant 2. So we can forget about the plus or minus and just simply look at 1 plus cosine theta over 2. This is the identity for our half angle. I didn't do anything. I changed it from A to theta. That's all. The nice thing is that they actually gave us what we need. They told us what cosine of theta is. It's 2 over 3. So this will be, did I write it down wrong? I did. It's minus. Minus. It'll be 1 minus 2 over 3 all over 2. One take away 2/3 will give me 1/3 over 2, which is 1/6. Because if you're dividing by 2, it's the same thing as multiplying by a half. 1/3 times a half is 1/6. But this leaves us with a radical in the denominator, so we can't deal with that. So we must rationalize our denominator by multiplying the top and the bottom by radical 6. One times radical 6 is radical 6. Radical 6 times radical 6 is 6. When they tell you that cosine theta equals a number, and they tell you which quadrant you're going to fall in, then you're able to figure out your sine, your cosines, and your tangent of your half identities to actual numbers. Yeah, they're going to still have radicals a lot of times, but you can go ahead and simplify it out as far as possible. Questions on that one? On any of the steps? Okay, let's look at cosine. Cosine of theta over 2 equals, if we look at our identity sheet, it's plus or minus, but we've already specified that it's going to be negative because we're in quadrant 2. So I'm just going to write minus, and then it's the radical 1 plus cosine theta all over 2. So it's going to be very similar to what we just did. We have a minus, and then we have 1 plus cosine theta was 2/3 all over 2. 1 plus 2/3 will give me 5/3 over 2. And again, same concept. We have 5/3 divided by 2. That's the same thing as 5/3 times a half, which will give me 5/6. Multiply the top and the bottom by that radical 6 over 6. Negative radical 30 all over 6. Now, with tangent, we can go about this one a lot of different ways. We have 3 different identities that we could use, and all of them would work perfectly fine. We can also go back to using the definition of what tangent means. Tangent is sine over cosine, isn't it? And we just found sine, and we just found cosine. And so the way I went about it in my notes was I just noted that tangent of theta over 2 is the same thing as sine theta over 2 over cosine theta over 2. And since we just figured out what all those are, we can plug them in and we can simplify it from there. If you don't want to use that method, and that's totally fine, and you want to use one of the original identities, the identity that I would strongly recommend using would be the very first tangent one. And the reason for that is because the first tangent one with the plus or minus only deals with cosine, and that's the thing that they gave you. And so if you want to be on the safest route, use the identity where you know for a fact every piece of it, not one where you have to compute a piece of it. Now I say that, and then obviously I'm showing you one where I'm using a piece that I computed. So, I mean, you can do it either way. We found that sine of theta over 2 was radical 6 over 6. Cosine was negative radical 30 over 6. Trying to make sure I'm staying on the screen for you guys. That's radical 6 over 6 times 6 over negative radical 30. Radical 6 over radical 30 is the same thing as radical 6 times radical 5. Notice those radical 6's are going to go away, leaving us with a negative 1 over radical 5. But we have to rationalize that denominator. Negative radical 5 all over 5. One minus that would be 1/3. And you get the exact same thing if you use the identity. That very first identity that I was mentioning, the one that only deals with cosine. Tangent theta over 2 equals, we already know that it's got to be negative, so I leave negative out there. It'd be 1 minus cosine theta over 1 plus cosine theta. That's what our identity states. Well, cosine theta is 2/3. One minus 2/3 is 1/3. 1 plus 2/3 is 5/3. So this would be dividing by that, so we flip it and multiply by 3/5. Notice we get 1 over 5, which is, which is right back up here. And then we just have to rationalize it, and we'd get out to the exact same answer. So whether or not you use the definition of a tangent with your half angles, or you use one of your actual identities, you do end up getting the exact same value. Again, this way, actually in the blue, the second method is actually the safer method because it doesn't rely on you having computed the sine of theta correctly. What I would say is, regardless of which way you choose to do it on a problem like this, I would recommend checking yourself. You could do it using the definition of tangent the way we did it the first time, and then use your identity the second time and make sure that you get the same answer. If you don't get the same answer, then one of two things has happened. Either the algebra that you've done on one of those is incorrect, or you got the wrong sign. And that's kind of a way that you can check to make sure that you got your sign correct. But either method works, and obviously you get the exact same answer. Are there questions? Okay. We got two other types of problems that you can see using these identities. One is a simplify problem, and then we'll do one verify problem at the end. with our simplify problem, at least this first one, we have plus or minus the square root of 1 plus cosine of 12x all over 2. So thinking about the fact that we are in the half-angle identities chapter or section, which of our half-angle identities does that look a little bit like? Yeah, it looks a lot like our cosine of a over 2. Because cosine of a over 2 is plus or minus 1 plus cosine a all over 2. So if that's the identity that it most resembles, then that tells me that from this original problem, my a is 12x. Because it has the 1 plus cosine of all of this stuff in here, which would be my a. So that means, what did all of that equal? Well, it equaled cosine of a divided by 2. Well, if a is 12x, that means I have cosine of 12x divided by 2, which means this is equivalent to cosine of 6x. And that's all you can do. You can't actually compute what it is. We can't get an exact value because we don't know what x is in this case. So the most that we can do is we can simplify it by recognizing what it resembles, identifying what that implies the a would be, plug it in, and simplify it. So these ones hopefully aren't going to be super difficult. They're just identifying which identity it most resembles. So let's look at B. 1 minus cosine 5 of alpha over sine 5 of alpha. We got to figure out what in the world that looks like. Here's a hint. There's no radical in this one. So odds are you're going to use one of your tangent ones because 2 of your tangent ones don't have a radical involved. So if we look at our list, we look down here at our 2 half-angle identities that deal with tangent, this very last one says 1 minus cosine a all over sine a. That looks a lot like what we've got. So if that looks a lot like that identity, then what is my a in this case? Yeah, the 5 alpha. So if all of this jazz right here with our a's equals tangent of a over 2, then that means we have tangent and our a is 5 alpha over 2. And there's nothing else for us to do. We can't simplify 5 divided by 2 any further unless we get a decimal, which we don't want to do. We just want to leave it like that. So I think the simplify problems are pretty easy. We good on those? Not too bad. All right, let's do our verify problem. We've done verify all week. Hopefully we're getting more comfortable with how to look at these and how to play around with them, even though they're all a little bit different. And obviously if we're in the half-angle identity section, we're going to be using some half-angles. So we have sine of x over 2 plus cosine of x over 2 quantity squared equals 1 over sine of x. One of our hints from previously in this chapter stated that when you don't know what to do, play around with the more complicated side. I would strongly agree with the fact that this side on the left is probably a bit more complicated because we've got half angles going on and we're squaring stuff. Another helpful hint is when you don't know what else to do algebra. So I have sine of x over 2 plus cosine of x over 2 quantity squared. That means I have sine of x over 2 plus cosine of x over 2 times sine of x over 2 plus cosine of x over 2, which means we should FOIL. FOIL means first, outer, inner, last. So if I do my first, I'm taking sine of x over 2 times sine of x over 2. That gives me sine squared of x over 2. Notice that what's inside of my sine is not what's changing. I'm taking sine times sine, which gives me sine squared. If I do my outer, I'm taking sine times cosine, so that'll give me sine cosine, like that. I get the exact same thing if I do the inner. Sine cosine. Then when I do my last, I'm taking cosine times cosine, which is cosine squared. These middle two are exactly the same, so I can combine them a little bit further. Sine squared x over 2 plus 2. We have 2 sine x's, cosines. Then we have the cosine squared x over 2. Now, what do we know about sine squared, cosine squared? If I'm looking at sine squared plus cosine squared, it does equal 1. So all of that stuff equals 1 plus 2 sine x over 2 cosine x over 2. We're getting really, really close. Now we need to figure out, what does this 2 sine x over 2 cosine x over 2, what does that look like? I'll give you a hint. It looks like something we learned in 5.5, which was called the double angle identity. So if you look at your paper or your notes from 5.5, which was the last lecture, notice 2 sine A cosine A. This would be the same thing as sine 2A. Well, what is A, though? Yeah, it's going to be x over 2. A equals x over 2. So then when I write this as, we saw that 1 out front, sine of 2a, instead of writing a, I'm going to write x over 2. Two times x over 2 gets me down to 1 plus sine x, which was where we were headed. So this one dealt with half angles, but we didn't actually deal with our half angle identity. What we used was our Pythagorean identity, and then we used one of our double angle identities in order to simplify it down. And that's where the playing around comes in with, you don't have to memorize all your identities, but you have to be able to look at them and say, okay, well, this looks a whole bunch like this double angle one, even if it's slightly different in terms of the fact that we have half angles in there instead of full angles.